right, so that's all done. I'm going to turn off our .network here, and let's do a quick flipbook of the actual result here. And I'm not really going to wait for it to finish. I'm just going to say the spray is what we're targeting, which are again these red areas, and you can see it's now kind of taking longer to drift down. It's being left behind. Like as soon as those droplets leave the main body of water, they're kind of getting caught by the wind because they're very, they're very small, and the wind kind of takes over. It doesn't have the same mass anymore to persist against the wind. And again, we can see some little eddies and movement in there as well. So we can be assured that it worked. To drop into our whitewater here, we have those three attributes that we've talked about. Bubbles, spray, foam, there they are. We're going to use those to split out the various things that we want to target, because we need to render them in different ways. The bubbles will be in the actual splash ocean surface. The foam will be turned into volumes, how we did in liquids 2. And the spray, actually, we're going to resim, or we're going to use the spray particles as a source to do yet another simulation. But it will be well worth it, because we're going to be able to add many, many more particles, so it'll look more like spray and not just, big old spheres. So to do this, we use the group syntax, where you just say at without any, attribute type before it. We just say at spray when it's greater than 0, and say points, and then you delete non-selected. And so this is the stuff that's considered the spray. You can see even after it lands, it's still being considered spray. If you do like 0.1, you'll knock out most of that. Because it's not, the spray is a number from 0 to 1, as you can see. I'll just say spray is 0 here for now. We can modify it later when we do our actual spray resimming. There we go. That's enough for now. Let's copy this one. We'll do, this one can be foam. So similar thing with the foam, where there's some overlap with the spray, but we get the idea. And a similar thing where you can do that to knock out some of the spray stuff. But this should actually probably be fine. And the other thing we want is the bubbles. The bubbles will be the easiest one, because we're really not going to do anything with the bubbles. In fact, it doesn't really seem to be, or I think it's bubble. That's why there's nothing there. There we go. The bubble will just be something that we see underneath the surface of the water. And we'll do that in the next chapter. Now, an interesting little thing to realize about all of this is, we simulated this on a flat tank. The surface is flat. So the result here is also flat. But if we need this to show up on our ocean surface, it's disturbed. At least for some of the other stuff we've talked about on our ocean surface, like the foam, because we are plugging it into the material, it's going to do its own displacement. But if we're going to render the foam on its own now, it doesn't know anything about that. So we need to basically move it ourselves based off of the spectrum and masks and whatnot. Now that's going to apply to both the bubbles and the foam, because they're both on or in the water. The spray itself is in the air, so it doesn't really matter as much with that. So we've been using the ocean evaluate a lot, and I want to show you an alternate way to do this, one that's maybe even a little bit more robust, and that is using a point VOP. The underlying technology of the evaluation of the spectrum volumes all goes through some VEX things, and in this case a VOP version of it called ocean sample layers. So an ocean sample layers asks for those same two things we've seen before, which is the spectrum volumes and the mask volumes. So let's promote these two to the top. We're going to plug in the values we expect. Let's plug in this downsample, and downsample, as I explained before on the ocean foam, basically says I know this is a resolution 9 thing, but treat it as a 8 or a 7 or whatever to knock out the little waves for whatever reason. So much like any other kind of noise, this is going to calculate based on some incoming position and time. Let's see if I can find it. There you are. It's going to calculate for every point here displace it, and come up with a displacement amount. So we just add that displacement amount to the original position. So there's the original position. Here's the displacement amount, and you can see it says displacement there. And then there's the new position. Now it didn't do anything because we didn't actually fill in these things yet. So I'm going to go over to the material here and just steal it from them. So I'm literally going to copy and paste these to here. I'm not linking them over because they already are links. You can see it already moved, but that's because it's look how crazy it looks. It's applying all of the spectrums on top of each other, but with no masks to say where to apply which to what location. So here's our masks, and now it should go back to looking normal. And there you go. It's a similar kind of thing as before, where the stuff up here shouldn't move as much, or not at all in some cases, but the stuff that's resting on the surface here, it certainly is. So we'll just label this ocean displacement. I haven't been labeling too many of the nodes in this lesson. I'm going to do a down sample of 1 to knock out the little tiny bits of waves, because maybe this foam wouldn't necessarily completely react to every tiny little wave that passes underneath it. But otherwise, I think we get the idea. So again, this is almost nicer to use than the ocean evaluate, because now we know that we're in sync. The same files that everything else is reading for the, in particular for the materials, we know that it's behaving the same exact way here. We can be sure of that. So cool. So we've got them actually displacing now. Now let's talk about the foam and turning this into a volume that we can render. This is going to be similar to what we did in the Fluids 2. In fact, it's very similar even to the shelf tools. They pretty much got it right there, which is we need to come up with some density values for these foams based on various criteria. And then those density values is what we'll use to actually make the volume. So I'm going to say, let's come up with an age first, which will be based on the actual age. And we'll say from age goes from 0 to, got weird for a second, 0 to fade, we'll say fade in, something like that. So from it being born to some amount of time, ramp it in. So go remap it to 0 to 1. And then we'll take that, we'll take that amount, age, and remap that just for maximum, we'll say density by age. And we'll remap that using a nice little ramp if you need to. So we'll just start there. It's probably fine to just have it come in like that. You can do the curvy graph with the Catmull ROM splines if you want. You might be interested in being like, oh, well, maybe it should ramp in like that. I mean, again, this is just tweaking stuff, but we'll leave it at the defaults for now. What's also, as another way to scale the foam out, we'll do the depth. We want it to be maximally foamy right on the surface. We want to ramp away from it as we go deeper into the water and as we go up away from the surface. So we'll say from the depth minimum to the depth maximum. We'll also remap from 0 to 1. So say the depth also can pass through a ramp, and we'll call that density depth, like so. Now that ramp is going to look a little different, because like I said, we want it to start at 0 when it's too deep, go to the maximum, we'll do that right in the middle, and then when it gets too high, come here. Also going to make sure these are Catmull ROMs again. Once we're done with all this, we'll actually fill in these actual numbers. But so those two parameters come together to make the density. So age times depth. And for fun, because this is the way that the shelf tool does it, I'll make the alpha be the same thing. So okay, so we've got something here. what's first? The first thing to me is the fade in of time. So we'll say, you can see these particles are brand new right in the beginning, but if they fade on over some time, you can see we see a little bit of a fade now. So I'll just say 0.5, and the depth is probably is fairly arbitrary. I'm going to go from negative 0.5 units below the surface to 0.5 units above the surface. And we have something. It's hard to tell just from looking at the points. I mean, most of this foam is already just sitting on the surface, so I don't expect this to do too much. But now that we have all those density attributes, which we could have also just visualized by clicking on density. We're in density mode here. There we go. Very cool. Let's actually just turn it into a volume now. So volume rasterize attributes, like so. The voxel size is 0.1, and we might be tempted to link it back to our liquid sim and stuff, but we don't really need to. This is fairly arbitrary to us. I would say that it should maybe be roughly based off of the actual whitewater itself, because that does at least determine. I'm going to go into disable simulations now. It should at least be based kind of off of the whitewater, because that specified how many particles we even had in a given voxel. So, oh, there we go, whitewater solver. So I'm going to grab the voxel scale, bring it here, like so. And I'm going to say it's the density attribute that we're interested in. So there it goes, it's showing up now. And we can actually make, we could do like 0.75 times that, which again is something that you'll see done by the shelf tools. It can be nice because combined with making the particle scale a little bit bigger, we'll feel a kind of a rounder aspect to it. Every point will be significantly larger than its voxel. So it won't just be one point filling up one voxel. Also a good idea to use this attribute rules thing down here and say, in case you have multiple points within a voxel, they should accumulate each other. It shouldn't just be that the voxel is on because it has any points in it. If points are bunching up in a certain area, I do want it to feel thicker, so they should accumulate, which is not the default behavior. So there you go. So now we literally have foam. You can see it has to think about that ocean displacement every time. It's not super cheap because there's a bunch of those spectra in there now. Awesome. What else might we do here? We could apply the actual motion blur to it. I believe we could add the velocity that this comes with to our incoming velocity. I don't think it's going to really make too much of a difference, but I'll do it anyway. So we'll say velocity incoming, add the velocity from here. Because remember, it has velocity from the simulation, but then it might get some velocity from sitting on the surface of the water too. I think the camera move alone will probably be enough. But for the record, this is more accurate, so we might as well do it right. And on our volume rasters attributes, we can do a velocity blur. So velocity blur always wants to do a shutter offset of 1 for some reason. That means look to the next frame. To me, velocity blur instinctually should be looking at the previous frame, or moving backwards in time. Again, not a huge difference, but it's more perhaps technically accurate. So that's the density. We also need the velocity that we just talked about. So turn off velocity blur for velocity. Let's rasterize the V attribute. We can keep all the rest of it the same. Oops. I guess we don't really need the accumulation. And let's take a look at it. Let's see that it do a volume slice just to see the velocity. It's representing the x, y, and z of the velocity as r, g, and b. So we can be pretty sure that it's right. It's not like there's no colors here at all or they're too big or something. We can see it's pretty much right around, you know, where it would be. It's like a cross section of it. You can always do the volume trail to totally see the vectors, like so. Okay, cool. We'll just put this off to the side a little bit. So great. So we have density, and velocity fields. So we can render this with there is actually a foam material for us ready to go. So I'll say out foam here. We'll run out here, we'll do a render foam. Or I guess I could say render whitewater foam. I'm just gonna say render foam. And that can point to this. Cool. This needs to get its own mantra node. Move this over so we can see our stuff easier. Mantra foam. Mantra foam doesn't care about this take thing. Mantra foam only cares about foam. So that's going to be the render foam that we just came up with here. Like so. Don't care about that phantom business. And that should pretty much do it. Oh, we have to put the material on it still. So go find what's it called? I guess it's just called whitewater. There it is, basic whitewater. So drag that over here, give our thing here the whitewater. Cool. So I'll go back to our favorite frame, which is frame 72. Okay, save it, render view, choose our foam here, and let's see what that looks like so far.